You ever look around and realize that the world isn't made of the perfect, smooth shapes we learn about in school? I mean, coastlines are jagged, clouds are lumpy, and lightning, well, it definitely doesn't travel in a straight line. For hundreds of years, our math has been amazing at describing the smooth stuff, but it's always struggled with the messy, jagged reality of nature. So what if I told you there's a new kind of math, a kind of secret language, built just to describe that beautiful, jagged chaos? Well, that's what we're diving into today.
All right, so here's how we're going to break this down. First, we're going to look at a really cool puzzle that basically breaks traditional math. Then, we'll meet its solution, F-alpha calculus. We'll see how it's kind of like a remix of the calculus you already know, and then check out how it's already being used to model the real jagged world. After that, we'll uncover the secret trick that makes it all work so elegantly. And we'll wrap up by asking a pretty profound question about the nature of time itself.
Okay, so why do we even need a whole new kind of math? Well, to get that, we've got to see where the old math just falls apart. And believe it or not, it all starts with a very peculiar staircase. Take a look at this. It's known as the Cantor staircase function. Now, it's obviously going up, right? It starts down on the left and ends up high on the right. But look closer. The whole thing is made up of perfectly flat, horizontal steps. It's somehow managing to climb without ever actually having a slope. I mean, if you remember anything from high school math, that should be impossible. For a line to go up, it has to have a positive slope, doesn't it? Well, apparently not.
This brings us to a super simple question that has a totally bizarre answer. How fast is it rising? If we were to use the language of calculus, what's its derivative at any given point?
And here's the punchline from standard calculus. The rate of change is 0! Almost everywhere. Why? Because pretty much any point you pick lands on a flat line segment where, by definition, nothing is changing. So our math is telling us the function isn't rising at all, even though we can clearly see that it is. Our tools are broken.
But you know, when your tools break, you don't just give up, you build better ones. And that's precisely what mathematicians Abbe Parvate and Adi Gengal went and did. They came up with F-alpha calculus. It's a whole new system designed from the ground up to deal with these strange, jagged, fractal shapes. This is a calculus for a world that isn't smooth, a world where things happen in sudden jumps and then long pauses. You know, like a stock market chart, or how a rumor spreads. That's the messy, real-world F-alpha calculus was made for.
Now, I know what you might be thinking. A whole new calculus? That sounds intense. But here's the really brilliant part. It isn't a total replacement for calculus. It's more like a remix. It keeps all the same core ideas, but just swaps out one very crucial piece.
So, regular calculus, right? It basically uses a simple, straight ruler to measure change between 2 points. Easy enough. But F-alpha calculus does something genius. It says, forget the straight ruler. Instead, it uses a jagged ruler, one that's shaped exactly like the staircase itself. It's like deciding to measure a crinkly coastline with an equally crinkly string. It just fits.
And this is the really beautiful part, a kind of poetic justice. That crazy staircase function, the very thing that broke our old system, in the new system, it becomes the fundamental measuring stick. The problem literally becomes the solution. How cool is that?
And you can see here just how deep this remix goes. For every single concept in ordinary calculus, derivatives, integrals, even the big fundamental theorems, there's a perfect mirror image in F-alpha calculus. It's like learning a new dialect of a language you already speak. It feels new, but also strangely familiar.
Okay, so the theory is pretty cool. But why does any of this matter outside of a university math department? Well, because the real world, it turns out, is full of things that look a whole lot more like that staircase than a perfectly smooth line.
With this new math, we can finally build accurate models for all kinds of jagged phenomena. Let's take subdiffusion. It's a fancy term for how particles move around in a super crowded place, like inside a living cell. They don't just float along smoothly. Nope, they get stuck, jiggle around for a bit, and then suddenly jump to a new spot. With F-alpha calculus, we can finally describe that jerky, stop-and-go motion, which is huge for things like figuring out how to deliver medicine directly to a cell.
And here's what that actually looks like. In a textbook, decay is always this nice, graceful, smooth curve. But in reality, in a lot of complex systems, it's a series of sharp drops and long, flat plateaus. It's a process that happens intermittently. For the first time ever, we have a type of calculus that can perfectly describe this jagged reality, and that is a total game changer.
And this is where things get really, really wild. We've seen that some things in the physical world happen in these jerky steps instead of a smooth flow. So what if that's true for time itself? What if some processes don't unfold in a continuous stream, but only happen at very specific, fractal moments in time, just sitting still in between? This sounds like science fiction, I know, but phi alpha calculus gives us the language to actually describe it mathematically.
So does this mean physicists now have to learn how to solve impossibly complicated new fractal equations? Well, amazingly, the answer is no. And that's because F-alpha calculus comes with a ridiculously clever secret weapon.
Yeah, its creators found what is basically a mathematical Rosetta Stone. They figured out a way to translate these hard, jagged problems from the fractal world into the smooth, easy problems of the ordinary world. You just solve the easy version using the tools we've had for centuries, and then you translate the answer back. It's an incredibly elegant shortcut.
And here's what that decoder ring looks like in the language of math. Now don't worry about the symbols here, just get the main idea. The top row, that's the complex fractal world. The bottom row is the simple ordinary world we know. And those arrows? They're the secret passage between them. It's a mathematical guarantee that you can hop back and forth between these two worlds without losing any information. It's just a beautiful and powerful idea. So the whole trick is this elegant four-step dance. 1. You start with a really tough fractal problem. 2. You use this defractalizing map to zap it into a simple problem you already know how to solve. 3. You solve the easy one using regular old calculus. And 4. You use the fractalizing map to bring that simple solution back into the real jagged world. It's an absolutely brilliant technique. Okay, let's zoom out for a second and just think about what this all really means. Because this is so much more than just a clever math trick. This really is a fundamental shift in how we can see the universe.
For over 300 years, calculus has given us the language for a smooth, predictable world. And that's been unbelievably powerful. But F-alpha calculus, it finally gives us the language for the world as it so often really is. Jagged, complex, and evolving in sudden bursts.
So ultimately, this isn't just about a new way to solve equations. It's about getting a new lens to see the world through. A lens that lets us appreciate the beauty and complexity of reality in its true fractal form, without having to sand down all the interesting edges just so our old math can handle it.
And that leaves us with one final, mind-bending question. We all tend to think of time as a river, right? Flowing smoothly and constantly. But what if that's just a useful approximation? What if on some deep, fundamental level, reality only actually evolves on a fractal set of moments? Thanks to F-alpha calculus, that's no longer just a cool philosophical idea. It's a question we can finally start to ask using mathematics.